Okay, so hello everyone. So we start the class. So at first, I would like to have one note on homework. Actually, there is a typo. So I would like to show it. Okay, so this is homework 1. So we have 3 questions. And question 3C. Yeah, so make the scatter plot for TV and cells and draw a fitted line over the scatter plot. And the original file said the scatter plot in A. And I have no idea why I put in A. Probably it was just a mistake by cutting and paste something. So just the C is a scatter plot for TV and cells only. So for that, just a simple scatter plot. On that simple scatter plot, you can put a line over the scatter plot. So line can be put by AB line function. So yeah, for example, just a quick instruction. So suppose we have X, the X, maybe just, this is just the example. So random numbers I make. Maybe Y is maybe 2 plus, maybe 3 times X plus, maybe random numbers. Then plot XY. We have this one, and we can put the scatter the regression line with specify. So we can put a straight line by putting by overlaying AB line function. So this means the Y is equal to 1 plus 2X. Okay. Then you can see that this is the 1 plus 2X, right? So 0 is equal to X is equal to 0, Y is equal to 1, and X is equal to 1, Y is equal to 3. So you can see that this is the straight line of Y is equal to 1 plus 2X. Then you can put in this way the regression line over the plot. And also you can do the AB line and the name of the linear model. Then the linear model has intercept and slope, so you can overlay the line over a scatter plot. Okay, so yeah, so just a typo. So just the scatter plot. So in A, that we make the pairwise scatter plot. So that is, you know, we have the several scatter plots, the TV, radio, newspaper, sales. So we have 4x4 scatter plot. So we have 4x4, so 16 diagonal part are just the blanks. So maybe we have 3 plus 3, so sorry, 6 plus 6. So 12 scatter plots in one window. So it's different. So in C, just you have to overlay the fitted line over this single scatter plot. Okay. So do you have any other questions on homework 1? Yeah. So so I asked you to do the homework in RStudio, and if you have trouble to create PDF file, you can see the sample file in a in Canvas, then you can mimic to the format. So important thing is that you put the code and output and figures in visible ways. So if you only submitted code, then I cannot really grade it. So I can see the code, but I would like to see the exact output that you generated from the code. Yeah. Okay, so if you have any questions, you can ask during office hours, or small questions can be asked by email also. I recommend office hours because you can get question in real time. Okay, so today I would continue chapter 3. We have some important concepts, and then we do chapter 3 lab. So this text basically is written as a self-contained textbook, and it does not assume the prior knowledge in R, but it does not explain all the the use of R from scratch, but just that they start with examples and the so it makes readers to understand how to implement code little by little. So after several chapters, I hope that everyone is comfortable with dealing with our coding for the materials. Okay, so chapter 3. So we start the collineality. Collineality is probably one of the most common problem when we fit the multiple linear regression. So last time we just finished before collineality. I think that I explained some. I explained some. But yeah, I think that we start with here. Yeah. So the concept is that when some predictors x1 to xq are nearly linearly dependent, that we say that there is collineality in predictors. For example, in economic analysis, you want to analyze the relationship between inflation and unemployment rate. And the unemployment rate have several definitions, maybe unemployment rate for entire people, or the number of people who cannot get full-time job, even if they want full-time. So different definitions have slightly different numbers. For example, some people have part-time job, but they want to switch to the full-time job, but they cannot find it. Then that percentage is larger than the actual people who are not working, right? So we have several definitions, but if the X, we use, for example, 5 different definitions of unemployment rate and say those are X1 to X5, then we regress the price, the inflation on those X1 to X5. All variables x1 to x5 are really similar, so it's really hard to identify the coefficients, right? So I had an example last time that the 2 dogs are, so you are walking 2 dogs, right? And the 2 dogs pull the leash almost at the same direction, then you cannot really decompose those into 2 forces. Right. So if the one dog pull the leash to the east and the other dog pull the leash to the north, then you can exactly see how strong each of the dogs is. But if the almost same direction, you cannot really see it. So that is basically collineality. So the basic question is that the linear model basically focus on minimizing errors. So estimated coefficients are a kind of the subproducts. So that's why we have difficulty to identify those coefficients. And usually it appears, so the collineality it appears when the variance, the standard errors of the coefficients are inflated. So to be exact, the coefficient divided by the standard error of it is very small. So the denominator gets inflated. So that is the usual phenomenon when we have almost linearly dependent predictors. So example. So this is credit data. So you can, if you wanna install, you wanna see the data, that you can install library, ISLR. Library and the package are the same thing. So basically we have some add-on to the default R, and the ISLR is package generated by the authors of this textbook. And the credit, data set in this library have this information. We have 400 observations of 12 variables, and we have income and the credit limit and the credit rating and I think the number of credit cards these 400 people have, and age of those people, educational level, probably the years of education, and the gender, and whether or not they're students, and married or not, and ethnicity. Have you ever applied for the credit cards? Anyone? No.
No.
No. Okay. So the students actually have relatively higher credit scores if you we adjust all other factors such as income level or something else, because the students means that at least the they are not poor in the sense that they can afford to spend more time to study or they spend tuition for study. So actually the risk is lower, and generally they are preferable. When I was a graduate student, I made a credit card with very low credit limits, but yeah, at least it's worth to try it. Yeah, so the student is another factor to determine, for example, credit limit. Yeah, so they're using this data set, then, okay, so we see several variables. So basically, we want to regress balance. The balance is I think the balance due, and age and the limit and the rating. So these are related to balance. For example, higher age. It's not clear, but maybe balance is maybe higher because they have credit cards for a long time, or I don't know. And credit limit is higher. Of course, we expect balance is higher. So suppose that your credit limit is $1 million, then you buy maybe, I don't know, the Range Rover, then it costs like the $100,000, then balance is higher. So limit is higher, probably balance is higher. Rating is higher, credit rating is higher. It's not clear balance is higher or not. Generally, balance is lower than rating is higher, but also rating is higher. That means that they use a credit cards a lot. So it's not clear what's the relationship. But if we see several, these three variables, these three predictors, we can see some correlation. The limit, credit limit, and age, these two are almost irrelevant as the data shows. Limit in probably US dollars and age in year, then almost irrelevant. But you can see the credit limit and the credit rating are almost correlation 1, have almost correlation 1. So higher the rating is, basically credit card companies allow you to use more, a larger amount. So the correlation is very high, probably I would say more than 0.99. So in this case, if we fit the balance on rating and limit, then we have inflated standard error or inflated variance of predictors. So these are two models. Age and limit are almost uncorrelated. So when we fit the balance on age and limit, okay, so these two are both significant. You can see p-values are very small. Coefficient negative 2.3 and 0.17, and standard errors relatively smaller to compared to these. So the t statistic is large in absolute value, making p-value small. So you can see clearly age negatively affects balance, and the limit positively affects the balance. Age negatively affects balance. Maybe it is consistent with so-called the life cycle hypothesis. So younger age, you don't have much income, but you want to spend more money, maybe for wedding or the buying the first car or something like that. And but anyway, they will earn in the future, so they can have a larger debt. And as you get older, you have to pay off all debt. Otherwise, you will bankrupt after you retire. So it's a kind of reasonable to have negative sign. So always see the sign of the coefficient to interpret the regression result. Only thing p-values are not enough. So age have negative significant coefficient, and the limit has positive significant coefficient. And also interpret age coefficient is negative 2.3. So as you get 1 year older, then the debt is $2.3 less. Maybe I don't know the unit, but the balance. What's the unit? Balance. I don't know the unit of this balance. You can see help of credit to see the description of these variables, the average credit card balance in dollars. So that means only $2.3. So if you are 20 years old and another person is 30 years old, the 30 years old person has on average the 2.3 times $10 more debt. So that is only the $23. So okay, so significant relationship, but the in reality, the number is not really large. Limit 0.173. So the credit limit is $1 higher, that you spend 17 cents more. That may be a more meaningful difference. So you have, for example, $10,000 higher limit, then you have $1,700 higher debt. So it has much larger impact, right? And actually the t-value is much larger, so more significant also. So practical difference is significant difference is different. For example, age 1 year older, $2.3 more debt. This is statistically significant, but practically it's not important. Okay, anyway, so that is the model 1 result. See the model 2. The rating and limit are predictors, and again, balance is the response. And rating has the 2.202. So credit rating is 1 higher than debt is $2.2 larger. Do you know what's the range of credit rating in US? Anyone? No. No credit card mania? No. I think that range is 200 to 850. So the lowest possible person, credit score and the highest possible score have 600 difference. Maybe the difference of maybe 50 or 100 is meaningful. Sorry, I got some chat. 01800. Yeah, 0 to 100. I think there are several scales. Yeah. Some scale is maybe 0 to 800, maybe FICO score, and the credit bureaus have the different scale. So we have some different some different scale. Yeah. So anyway, so maybe, okay, so 100 maybe meaningful difference. Then what's the difference of 100? Then 100 higher, then the debt is $220 higher. That makes some sense. That makes some sense. So so it's maybe practically meaningful. And the limit, that was very significant in the previous regression, but here the coefficient is 0.025 and the standard error is 0.064. So it's very large. So t-statistics 0.384 with p-value 0.7. So this model, that means that the credit limit is not a significant factor to determine model 2. Also, coefficients gets much smaller. So what this means? So basically the rating and limit. So these are really related. So these coefficients are not reliable. So 0.025, possibly it's larger, or basically these two have basically the similar things. So it's not really meaningful to divide the effects of these two factors. So the coefficient is less meaningful compared to the previous regression, and the standard error is inflated compared to this. So this is not really the reliable to see if the limit is important factor to determine the response, the balance. And so this is the conceptual graph on what's happening there. So this is for the first regression, the balance on age and limit. And this is the regression for the balance on rating and limit. And first regression, age and limit have lower correlation, almost the independent. In such a case, this contour plot of combination of the beta hat age and the beta hat limit is this. So basically, beta hat age and the beta hat limit are not correlated each other. Okay. Yeah. Yeah. So these are, not age and limit itself. The coefficient, the estimated coefficients have the smaller correlation when these variable themselves have lower correlation. So in such a case, maybe the interpretation is just normal. But for rating and limit, we have high correlation. And in such a case that we have higher correlation on estimated coefficients of rating and estimated coefficients of limit. So actually, the estimated coefficients are distributed in this way. So that means the beta limit may be much larger, but in such a case, the beta rating should be much lower, right? So it's maybe good to use the example of the two dogs, right? So two dogs pulled a leash at the same direction, almost at the same direction. And okay, so you decompose those two forces. One is maybe, I don't know, maybe some 10 Newton meter, and the other is 5 Newton meter or something. But maybe your decomposition is wrong. 10, you thought 10, but that was actually 2. In such a case, the other one, 5, there should be 13, right? So if the one is underestimated, then the other should be overestimated. So that is the situation happening here. So even though the profile have very large variability, so beta limit may be as small as negative 0.15 and as large as 0.2, and the beta rating also has wide variability. Maybe it is as small as negative 0.5 and as large as positive 4.5. But if beta limit is overestimated, then beta rating should be underestimated. In that sense, that we estimated the model pretty accurately in some sense. Okay, so a kind of the summation of the beta limit and the beta rating are in narrow range. Maybe to be exact, some constant times beta limit plus the beta rating is in a narrow range. So that is what's happening. So in this case, even though regression result isn't bad in the sense that this contour doesn't have a large area, but if we see just each estimator, each coefficient, then it has wide variability. So that is happening here. And okay, so now what's the problem? Okay, so we know the variable. So and we see the description of relationship between betas, so we can see what's happening. But we cannot see multi-collinearity if we just look at this table. For example, if you see some applied papers in statistics or economics or any other fields in natural sciences or social sciences, then you can only see this table. And how you can tell the variance is inflated, multi-collinearity happens. And actually, if we see only this table, that we cannot really tell. But if we calculate additional statistics, we can judge if there is multi-collinearity. So the concept is the variance inflation factor. So how much variance is inflated compared to coefficient. So yeah, so basically the variance inflation factor that represents how many times the variance of beta hat j gets larger relative to squared residual standard error. When the model changes from this to this, maybe it's a little hard to see, but okay, so we think about the simple linear regression with xj as the only predictor. And the other one, we have many other predictors. So maybe the first one, maybe xj is the limit, maybe credit limit. So just we fit balance on limit. And the other one, we have many other factors, the age or credit score and so on. So in such a case, the impact of one variable gets smaller and it becomes much less significant. So we want to see how much variance was inflated. Yeah, so variance inflation factor. Okay, so and the variance inflation factor is actually calculated by this formula, 1/1 minus the multiple square of some regression model. So what regression model? So this is the regression, the multiple R square when we regress xj on the other x variables, x1, x2, up to xp, except for xj. And okay, so the reason is not clear, but we will see just with numerical examples that this is the correct formula. If the variance is inflated more than 10 times, or standard error is inflated more than 3.2 times, square root of 10 times, then the people say that the multi-collinearity is regarded as severe. So 10 is not a magic number, so but just as a ballpark estimate, that we have 10. Okay, so just see what's happening here. Okay, so balance on limit. So this is the regression result. The t-value is 33.8, very high, p-value very small. Estimated coefficient 0.17 and standard error 0.005. If we put these three predictors, the limit has much smaller coefficients. The 0.17 becomes 0.019, almost maybe 9 times smaller. And the standard error, that is the square root of variance, that becomes 0.005 to 0.062. So that becomes 12 times larger. Yeah, then the coefficient, the ratio of standard errors. So we have seen that 0.0696 and 0.005. So the ratio. So this is called basically the square root of variance inflation factor. But we normalize this by standard error. So residual standard error is basically dominates every standard error. So the it's reasonable to standardize this by the residual standard error. So we divide the 0.005 by this 233 and this 0.0629 by 229, then take the ratio, then we get the 12.67. So standard error is inflated the 12 times. And the variance is square of standard error, so take square, then 160.58. So variance inflation is very significant. And this number is also obtained by the VIF function. We have to use another library, the CAR. I don't know what CAR means. AR maybe probably autoregressive. And the VIF. Variance inflation factor function. Then we put the linear model. If you have already named this linear model, just you can put that like LM1. And then we can get the variance inflation factor is 160.59. Also rating, we have very large variance inflation factor. But age isn't really correlated with other predictors, so variance is not inflated much. So this is very clear-cut results, but usually the result is much more vague. And another way, so I said that we can use multiple R squared to calculate the variance inflation factor, and actually the magically 1 over 1 minus the multiple R square becomes the variance inflation factor. We don't prove this, but if you do some algebra, you can see that these two are the same. And here, the R squared, not adjusted R squared. So non-adjusted R square we have to use. Okay. Yeah. Do you have any questions about variance inflation factor? Okay. And some remedies for collinearity. What happens when we have multi-collinearity? And the first suggestion is surprisingly just ignore the issue. Okay, if you only focus on prediction. So as I mentioned that this happens because we focus only on the error size, right? So linear regression result focus on the error size. And in terms of the error size, it's already minimized. So we don't really have to worry about the multi-collinearity if your interest is only for forecasting. Yeah, so for example, yeah, so think about the two estimation of one linear regression. So we fit Y on something. Maybe Y is equal to, okay, so one estimation is maybe 2.0, the plus 3.1 times x1 plus maybe 1.9 times x2 plus epsilon. And suppose that for simplicity, x1 is almost the same as x2. And estimation 1, maybe from one data set. And estimation 2, so the same estimation from the other data set. Then we got, for example, maybe 1.9 plus maybe 0.2x1 plus 4.8x2 plus epsilon. Okay, so you can see that the situation is terrible. So these coefficients are much different, and these coefficients are much different. But if x1 and almost equal to x2, basically this part 3.1x1 plus 1.9x2. So this is almost 5 times x1 or 5 times x2, right? And also this time 0.2 times x1 plus 4.8 times x2. This is also almost 5 times x1 plus 5 times x1 or 5 times x2. Right. So in terms of forecasting, it doesn't have a problem. So the result is pretty stable. So in terms of y hat, it's not affected by multi-collinearity. Yeah, but sometimes you want to really see the effects of each variable. So in such a case, exclude similar predictors beforehand. So you can decide whether you use x1 or x2, maybe more meaningful ones. Then if you use only x1, always you would get y is equal to 2.0 plus maybe 5 times x1 plus epsilon. And it does not depend on data much. So if you drop one of the variables, then it becomes much stable. Yeah, and also more automatic ways, for example, the combine similar predictors beforehand. So you can calculate the common movement of x1 and x2 by some methodology such as the principal component analysis or state space models. We haven't covered it, but the basic idea is, for example, the average of x1 and x2, that may be, a kind of index to express the all predictors. Then you can use it in the prediction. I mean, in a regression. And maybe more automatic ways use a variable selection method, which drops more variables. So lasso regression, rich regression, we will cover these later, but these methods drop more variables. So we keep less number of variables. So we can identify which predictors are significant. And another one, also the structural equation modeling. So this method can identify which predictor is more significant to the response. Yeah, in a multiple regression setting. So the multiple linear regression focus on basically prediction. So focus on minimizing errors. Structural equation modeling, we have, so the interpretation is more important. So interpretation focused method. So we have, for example, if we have two predictors, that we have this kind of the diagram, and we can see that how much impact x1 has on y in this way. So what's the direct impact? What's the amount of direct impact from x1 to y, and impact from x1 to x2 and x2 to y? So in this way, you can also calculate the total impact of x1 or something. Right? So if x2 comes in, then x2 explains almost everything, but this may be large impact, but also we can calculate the indirect impact of x1 to y, so that we can see the total impact of x1. In some model, it's even possible to see which direction is true. x1 affects x2 or x2 affects x1. Maybe we need some additional assumptions, such as x1 is affected by z1 or something like that. But yeah, so structural equation modeling is more useful to see significance of coefficients. We don't cover it in class. Okay, so do you have any questions? So this is the last slides for collinearity. Yeah, so if you want to see if the impact is significant, I would recommend you to do simple linear regression first. Then you can see whether two variables, y and x, has significant relationship. Okay. And multiple linear regression is more the prediction forecast method. So if you want to explain more of the variation in y, it's good to put multiple variables in the model. But the meaning of coefficients become vague. Okay, so next, the qualitative predictors that we discussed it in the earlier chapter, but also we discussed some implementation in R. Yeah. Do you have no questions so far? Okay, so so this is the property sales data. So I downloaded a few years ago, so that's why the price of houses are cheaper. 140,900. I think probably this is all by level. Yeah. So this is the property sales data. Yeah, in Troy, Michigan. Now the price is much higher. This is just after the financial crisis. And we have several factors to determine price: the year built and the square footage, bedroom, number of bedrooms, the number of bathrooms, and maybe style also. And okay, so now that we think about the number of bedroom, okay, so it may affect price. Yeah. The number of bedrooms is either 0, 2, 3, 4, 5, or 6 in this data set. There are no observations with one bedroom. And it can be regarded as either quantitative or qualitative. Okay. What does quantitative means? That means the 6 bedrooms is, the 3 times the more bedrooms than 2 bedrooms. So these are quantitative. 4 is between 2 and 6, just in the middle of 2 and 6. And qualitative means that the relationship between price and the number of bedrooms is nonlinear. For example, bedroom is 0, then that house is useless, you feel, for example. Then we have much smaller value. But the number of bedrooms, the 5 and 6, maybe it's annoying to have 6 bedrooms if you only have 3 or 4 people in your household. So maybe the more bedrooms is worth more, but the 6 bedrooms, actually it's worth less. That's possible, right? So that kind of nonlinear relationship between the bedrooms and the price. So that is that can be modeled if we regard this as qualitative variable. So just use the dummy variable for 2 bedrooms, 3 bedrooms, 4 bedrooms, 5 bedrooms, the 1 variable each for each number of bedrooms. Then we can we can assume the nonlinear relationship between the number of bedrooms and the price. Okay, so basically we consider 2 models. So first model is here. So basically the number of bedrooms have linear impact on price. So beta 4 times number of bedrooms is price. So suppose that we have the 0 bedrooms, the baseline price is the $2,000, and the 2 bedrooms, then 240,000. Then number of 4, that should be 28. I mean 280, and the 6 bedrooms, the 32. So 320,000. So this is linear relationship. So this is the model 4. And model 5 that we have actually the additional setting here. So beta for I. So this is the indicator variable for the number of variables. So that means the this model 5 assumes that we have nonlinear relationship. So we have maybe the 0 bedrooms, the 200,000, and the 2 bedrooms, the 240,000, and maybe 4 bedrooms. We have only 260,000, and maybe 6 bedrooms, then 200 maybe 65,000 or something like that. So we have nonlinear relationship between number of bedrooms and price. So in such a case, we cannot use linear model. So we have to use this as the categorical predictor. So basically 2 bedrooms have the positive impact of $40,000. 4 bedrooms, the positive impact of 60,000, and 6 bedrooms, 65, and so on. Yeah, so maybe the model 5 is a little tricky because it also has this linear term. And actually, it's possible to delete this one. So just the factor variables, so beta for I. But I would like to know, we would like to know that if we have additional information for nonlinear terms. So we put still linear term, and we see if this is sufficient or not. I mean, the addition of beta for I has additional information or not. We would like to see if this term has additional information to linear term. So that's why I put both terms. And how to fit this? So the first model, the linear model, that is simple. So within LM function that we put price on the other variables: square, year, bathroom, and bedrooms. Right? And to add factor variables that we put this one. So as factor bed. So this is our basically matrix of indicator functions. So this yellow one is the as factor bed. So the number of bedrooms that we have. Okay, so baseline is 2. Then we have 2, 3, 4, 5, and 6 bedrooms. So some observations. So we have how many observations here? So we have, I don't know, maybe 150. No, about 1, 2, 3, 4, 5, maybe 490. 490 observations. So 490 observations, and we have indicator variable like this. Like this. So this is the as factor bed. Okay. Then we put this term at the end. Then the regression results are this. So the regression for this is just a linear regression. So we have the coefficient here. And actually the number of bedrooms has negative impact on the price. Do you know the reason? This is actually the robust result. If you use another data set, usually this has negative coefficient. Why more bedrooms, smaller price? Anyone can guess? I can give you some extra credits for your quiz score. Anyone? Anyone? How about Mira? Hello, are you listening? How about the Shiv? Shiv Patel? Sai?
Is it because it's already the square footage year and bath are
Yeah,
already?
that's true. Yes. So the square footage is already in the model. Yes. So if we just ignore all factors and we only know the number of bedrooms, the more bedrooms, the higher price. But basically the size of the house is already determined by the square footage. So we know that. Then more bedrooms means the bedrooms are just the boxes. So that means that we have less features such as the more bathrooms or a larger kitchen or something like that. So actually it worth less. Okay. Maybe in the future, maybe when you are asked question, you have to answer something. Okay, so answer something, even if you cannot get the answer. Right? So maybe I would take attendance in that way. Okay, so the number of bedrooms is significant factor and actually the negative impact. Okay, then now that we have different ones, so this is a little complicated. So we have, so this is the result. Okay, so these coefficients are the same. Okay, so the number of bedrooms that we have the much smaller amount, but we have other terms here. So it's harder to interpret this as a single factor. And we have the 4 additional levels. So it's a little hard to see, but originally we have 6 levels for bedrooms. Okay, so but if we include all indicator variables for these 6 levels, actually these are linearly dependent with intercept, right? So either of these 6 is true. So if we prepare all indicator variables, then summation is exactly the same as intercept. So this is linearly dependent. So 6 levels means the 5 degrees of freedom. Right. So basically we have 5 levels: F2, F3, F4, F5, F6. F0 is the baseline. So difference between F0 and F2, difference between F0 and F3, difference between F0 and F4, and so on. So we have 5 levels. But we have linear term here. So if we include linear term, actually the 5 degrees of freedom, it's too much. Actually, these 6 variables are linearly dependent. So we have to exclude one more. So that's why that we have only 4 additional levels. So this means that the baseline is bedroom 0. Okay, so baseline. So bedrooms 0 bed. Baseline 0 bed. And how about 2 beds? 2 beds, the impact is at first the bedrooms times negative 31. So 2 times negative 31,000. Okay. But the plus 83. So plus 86,000. 83.6. So the total impact is the positive negative 62, positive 83.6, so positive 21.6K. So actually 2 bedrooms that we have positive impact, the $21,000 more. So you can see, so Anyone else? So the 3 bedrooms, the value is higher than 2 bedroom or lower than 2 bedrooms. Anyone? Suppose we have the same square footage here and the number of bathrooms, 2 bed and 3 bed, which is worth more? Paula? Paula?
I'm sorry, Professor. I'm not feeling well today.
Oh, okay. Sorry about that. Rajesh? What do you think? The 3 bedrooms is worth more than 2 bedrooms or less than? Not sure. Okay. Anyone else? Oh, sorry.
Oh. They have the same square footage, right?
Yes.
So 3 bedrooms maybe is worth more.
3 bedrooms, it looks like, right? But actually not. So you can see you can calculate it. So the 3 bedrooms, this number looks larger, right? So larger than this, but actually the impact for 1 bedroom is also from the linear term. So that means the 3 times minus 31,000, right? And plus 1,009,000, right? So that is the 109 minus 93, so 16. So $16,000 more than no bedrooms. So that means that actually it's worth less. So 2 bedrooms has more value than 3 bedrooms. And 4 bedrooms, also the increment is 16,000. This is almost the same between 2 and 3, but actually the number of bedrooms, 1 additional bedrooms, negative 31. So actually the 4 bedrooms is worth $15,000 less than 3 bedrooms. And 4 and 5 actually almost maybe slightly positive impact. So plus 43, but the minus 31. So maybe plus 12,000. So 5 bedrooms worth a little more. Probably 5 bedroom houses have more luxury features, so that's why it boosts price. So bedroom itself does not add value maybe, but still in regression model it's worth more. Yeah, so yeah, and also we see the significance. What's the significance? So beyond linear term, so how this information is useful. How this information is useful. Then you can see the standard error of these terms, and you can see the t-value and the p-value. So that means, okay, so p-value is very small. So that means the nonlinear term also has a large impact. So probably it's good to use the categorical. It's good to use the number of bedrooms as a categorical variable, qualitative variables. Yeah, so the above result indicates that when we introduce a parameter for each level of bed, many of them are significant predictors of price. So probably this is useful. And we can test the significance by ANOVA. So analysis of variance clarifies whether predictors are significant overall. So the problem here is that we have many predictors, so we cannot really see the overall significance of the predictors. So for example, the year is significant variable and it has only one coefficient. So if this coefficient is significant, then year is significant. But the number of bedrooms, since it's split into several levels, so we are not really sure in total, so this group is significant or not. So in this case, p-values are all small, so we can see that it's significant. But if one p-value is, for example, 0.06 or something, and the others are 0.10, 0.20, 0.30, okay, so everything is a kind of small, at least less than 0.5, and the one is almost significant. In such a case, even if all variables are not significant, still it's good. Sometimes it's good to include this categorical variable. So we just want to have a criterion to judge overall this categorical variable is significant. And actually the ANOVA can do this, and the bedroom as a factor has additional information to these 4 variables. You can see, because the overall, the p-value is 0.10 to the power 5, so 1, 4, so 0.00003. So it's highly significant. It's much smaller than 0.05, for example. So it's meaningful to introduce the number of bedroom as a categorical variable. Do you have any questions so far? Okay. Okay, so next we go to we're going to review a little bit about AIC. So AIC stands for Akaike Information Criterion. I think everyone here but this one, maybe Sarah, have you heard of AIC?
I have not.
Not, okay. So AIC is the number to evaluate the regression model. Smaller AIC, the better regression model. That means that if we have another test data set, we expect that the forecast is more accurate. So AIC, Akaike Information Criterion. So Akaike. Information criterion. A smaller AIC, better expected fit for out of sample for test data. So the point is for the test data. So if we have many predictors, of course, the in-sample fit gets better, right? So we have 490 observations. If we have 400 predictors or 490 predictors, we can explain everything. So in such a case, of course, the in-sample, the training error is small, but the test error is small for smaller AIC. So better expected, maybe just test error. And the AIC is calculated by -2 -2 times log likelihood plus 2 times number of predictors. P is number of predictors, number of parameters. I think including intercept. Okay, so this is the AIC. So log likelihood is likelihood. So higher likelihood is better. Higher is better. And the number of predictors, actually the smaller is better, because the smaller number of predictors means the model is simpler. If we have the same performance, simpler model is better, so smaller is better. So that means, okay, so we have -2 sign here. So larger likelihood is better. So that means the -2 times likelihood, smaller is better, but also 2p, smaller is better. So if p is larger, then model is more complicated. So usually likelihood is better, larger, but the we have trade-off between these two terms. If p is large, then the second term gets larger. So it prevents the AIC to be smaller. So we have to balance between likelihood and the model complexity. The simpler model, but also the better fit. Likelihood is in-sample fit. So in-sample fit is better, but smaller model. Then we expect the test error is also smaller. So AIC is this. And yeah, so as a so software has maybe slightly different way to adjust this AIC. So we normalize this by sample size or something. So you may not be exactly getting the same number if you calculate this from scratch, but the AIC of linear model can be calculated for the two models. Maybe model 4 and 5, sorry, model. Yeah, so these 4 models, so 4 and 5. So I think these are typos. So model 4 and model 5. So remember that the 4, just the quantitative variables. So number of parameters are year, square footage, bathroom, bedroom, and intercept. So 5 maybe. And here the AIC. Sorry, the number of predictors is 5 plus 4, right? So this is from the categorical variable of bet. Okay, so this is 9, so it's larger. So AIC gets larger, but actually AIC drops 18. Right? So that means the second model is much better in terms of likelihood, and we expect the better result. So basically, we have the penalty of 2 in AIC when we increase one predictor. So 2 is a kind of the contribution of one predictor. Sorry, maybe just the penalty. So if one variable is totally useless, but we include it in the model, then we have the penalty of 2. So AIC lowers by 18. That is, pretty large amount statistically. So the model 5 is better than model 4. Yeah, the same analysis can be done for the number of bathrooms, and in fact, the number of bathrooms as a factor is also a significant factor to determine the price. Yeah, obviously you don't need the 10 bathrooms or 20 bathrooms, even though the number of bathroom has positive impact on price. Yeah, so that's. Yeah, so I heard from friends that one condominium has the just bathtub when you enter the building from the entrance door, and it's really strange that you enter the condominium, then just the one bathroom, a small bathroom with bathtub appears, and probably that happened because additional bathroom adds more value. So for developers, then more profit maybe. So that's why they put another bathroom. But yeah, the number of bathrooms usually add value, but actually the effect is nonlinear. So if you put 10 bathrooms in a small house, it does not necessarily boost the value. Okay, so do you have any questions? Okay, so 3D. Oh, and today's quizzes are almost on these ones. So one question on multiple lineality, multi-collineality, and another question about the variance inflation factor, and maybe the other about qualitative variable. So it's similar to this kind of thing. So I asked to do ANOVA using this ANOVA function. Yeah. So we have 3 quizzes. So remember that the quiz, the 127.3. So this is due February 3rd. So last time I gave this homework, but we didn't cover the material for collinearity, multi-collinearity. So we have 3 quizzes basically. So one is named as 127.3. So just be careful not to miss this. Yeah. Any other questions? Okay, so now the 3D, the last one. So removing additive assumptions. So suppose that we want to predict y by x1 and x2, and so far our standard model is this. But possibly we have interaction between x1 and x2. So we can put the x1 times x2 in as beta 3. I think that you can put I of x1 times x2 in R to include this term. I may be necessary, may not be necessary. I'm not exactly sure. You can try this. Yeah, so of course the general, logically we can put other variables such as x1 squared times x2 or something. But usually the lower degree terms are more significant, practically. So usually we start with lower degree terms. Maybe it's reasonable to put x1 square or x2 square at the same time. Once some students analyzed some real estate data in which the distance to the city center or distance to the train station is important, and the distance is represented by the second degree polynomial of longitude and latitude, right? So distance is usually the square term we include x1 and x2, and also it's not just Euclidean distance, but maybe along some major way. Maybe even if the physical distance is more, maybe access is easier. So that kind of geographic information can be included in the secondary, in the second degree terms. So the regression result, the performance improves when the students included the x1, x2, and x1 square and x2 square. So always think about the interaction. So these days we have many fancy models such as support vector machines, the tree regression models, neural networks, but often they're using interaction terms just solve the problem. Linear model with interaction terms sometimes performs better than support vector machine or neural network. So always you can consider including the interaction terms. Yeah, and okay, so this data set is really made well, the sales data, advertising data. so sales on the TV advertisement and the radio advertisement. And if we include the product of TV and radio, then this factor is actually significant with very high p-value. That means the very small p-value. And some other examples. It's very natural to consider interaction. For example, the crop yield may be affected by the amount of fertilizer only when sunlight is not enough. So usually, the crops grow as long as the natural condition is good. So, and maybe soil is good enough. But if the soil is bad and the sunlight is not enough, then fertilizer helps a lot to grow the vegetables, for example. So the interaction between the fertilizer and the sunlight is high. Sometimes it's possible. Or the southpaws pitch well only when the batter is left-handed. Okay, so think about the batting average based on whether batter is left-handed or right-handed, and also the pitcher is left-handed and right-handed. Okay, and okay, so probably the effect of this is almost zero, and the effect of this is almost zero. I don't know. Maybe the left-handed batter has slightly higher batting average, so maybe I don't know, the 0.01 something, and the pitcher, I don't know. Probably this is around zero, but you can see that if batter is left-handed and the pitcher is right-handed, then batting average is much lower. So that means the batter interaction pitcher should be significant. So pitcher is left-handed. Sorry, the pitcher is left-handed and the batter is left-handed. So both L, then probably the batting average is much smaller, maybe highly significant, maybe negative 0.1, 0.5. So highly significant, that's possible. Yeah, okay, so the almost we finished one, and 3 is not really much relevant to our earlier sections. So yeah, so we studied the several concepts today. So one is collinearity, and the other is the nonlinear effects, so non-additive assumption. Okay, so if you don't have questions, then that's it for today. So see you on Thursday. If you have questions, you can stay online.
Thank you.
Sure.
Thank you, Professor.
Bye.
Sure.